Welcome back to ECE 501B. The next time we meet will be the exam. We may have a few more participating in the class, so make sure that we're sort of every other seat so that we can get people in here and properly outfitted for the exam. I think I'll give you the exam process in a little bit, but there is review material again on D2L. Today what I want to do, although I almost forgot, is I want to just talk about this one last theorem in Chapter 3 as a wrap-up. You've had to use it, I think, on your homework, potentially, but it's talking about operators, and that's really these linear maps where your input domain and your domain and your codomain are the same. Your input vectors and your output vectors both are living in the same vector space, and that then results in some pretty useful properties. And that's what we will be playing with most of the remaining part of the semester. We will then go into Chapter 4, which that won't be on the exam, meaning the first part of today's class will be, but after or once we get into polynomials, we'll save that for exam number 2. We will simply summarize very quickly some of those points from Chapter 4 dealing with polynomials, and then we will try to spend the rest of the time motivating Chapter 5, which Chapter 5 now is dealing with eigenvalues and eigenvectors. And we aren't using any notion of a determinant in order to talk about eigenvalues and eigenvectors, which is the reason for the title of your textbook, Linear Algebra Done Right. We're delaying determinants until the end of the book, and we're talking or trying to motivate this concept of eigenvalues and eigenvectors differently than what you might see in a traditional linear algebra class. We'll try to motivate that with some examples showing the properties, some of the existence concepts or the existence of eigenvalues or not, and something about invariant subspaces, which is really what eigenvectors are. What do we mean by an invariant subspace? Before we do any of that, though, let's just remind ourselves this very quickly, and I'll just let you read this. I'm hoping you already know. You'll have 2 sheets of notes, front and back. You can bring a calculator and something to write with, but that's it. In terms of what the exam you will be expected or be expecting to see, it'll be consistent with the review or the practice exams on D2L. There's 5 problems. One of those is probably going to be a proof. You may have to show or demonstrate or produce a counterexample. You might need to create or build a vector space or matrices or basis, something to that effect. Let's now, before I forget, go into our Chapter 3 wrap-up, which is really dealing with this idea of an operator. Here, an operator is a linear map. In that sense, we're not doing anything new. We're actually specializing this linear map. An operator is a linear map from a vector space onto itself, meaning we now have this linear map T whose domain is a vector space V and whose codomain is also that same vector space V. And we might denote that, consistent with what we've done before with this script L, we'll actually abbreviate that. Since our domain and codomain are the same, we won't use 2 arguments on the script L. We'll just use the one that's common to both the domain and the codomain, meaning the set of all operators on this vector space V will be abbreviated from script L of V comma V into simply script L of V. As I said when we were first talking in today's lecture, in general, this is what we will be dealing with for the remainder of this book, our operators. We may break away from that a little bit, but in general, for the remainder of the course, we will actually focus on operators. And what I wanted to cover today before we moved out of chapter 3 is from the second edition, Theorem 21 in chapter 3. It says if V, and again I'm assuming that you're tweeting still, so if this vector space V is finite dimensional, if V is a finite dimensional vector space with an operator T on that vector space, and if you remember what we were talking about before, we were actually talking about invertible maps, whether those were injective, whether they were surjective. Now, once we're dealing with an operator, or when the domain and the codomain are the same vector space, those three concepts are actually equivalent, and that's what this theorem is saying. If V is a finite dimensional vector space with T an operator on that vector space, the following statements imply each other. The first statement is the linear map T is invertible. Statement 2, so if you know your map is invertible, if it is an operator, then you can know that T is injective. If you know it's injective, then actually T is also surjective. Question? So now the question was, if it's injective and surjective, is it an operator? It doesn't have to be. We've developed those concepts up to this point without specializing to a linear map being an operator. So we were having a domain and a codomain. Now what we want to do is go ahead and specialize that and say our domain and codomain are the same vector space. If that's the case, then if you know one of these three, you know the other two. That's the point of this. And typically it's easier maybe to find out or analyze a map and find out, does this have a non-trivial null space? Or is this an injective operator? Then if you can show that the only vector in the null space is the zero vector, then you know that your map is invertible and you know it's surjective. You know this operator is either of these three. Let's quickly sort of justify this, that 1 implies 2, 2 implies, so if you had to show, let's say that somebody said the following three statements are equivalent, which is essentially what we're saying in this space of having an operator, a linear operator, you would need to show, or you could show 1 implies 2, 2 implies 3, and 3 implies 1. Then you know you can get to any of them from the others. Let's sort of do that. So now, let's say the A part of our proof is, let's go ahead and assume that we have 1 is true. If one is true, saying that the operator t is invertible, then really all we have to do is go back to that earlier proof or theorem. 2 is implied by definition of invertibility. Meaning this actually follows from proposition 317, which said a linear map is invertible if and only if it is both injective and surjective. So if we have a map that's invertible, then we know that it's injective. So 1 implies 2. Therefore, T is injective, or 1 implies 2. In the second part, or part B, let's now assume 2. Let's assume that our map is injective. If the map is injective, what do we need? And now you might be thinking about what you need to do for the exam, and let's say that you're now faced with a proof. And one image that I like to sort of think about now that sort of come to me, I guess, recently is you've probably worked jigsaw puzzles. Now a proof is like a jigsaw puzzle. You have some pieces, you have facts. You maybe have A, you have B, you have C. Maybe B tells you some other facts. And so you can put those facts on the table. A might give you some more facts. You have now a bunch of pieces, many, many facts. Now you need to try to put them together. Meaning when you're putting together a jigsaw puzzle, you may not start from the center and work your way to the end in one smooth progression. You may have to start building different parts that fit together, and boom, now all of a sudden they're starting to fit together. And then you can start playing the tape forward and saying, here's my proof. One thing to keep in mind when you don't, how do I want to say this? I think when I was first thinking about proofs, I thought you have to know how this happens linearly from the beginning to the end, and that's probably not how everyone does proofs. They don't know magically how to go from beginning to end. They have to sort of start at the beginning, start at the end, gather some facts, gather some puzzle pieces, and start putting them together and then seeing how they fit together. That's maybe something to keep in mind as far as when you're dealing with proofs. Back to this proof, now we're assuming 2. We're assuming that T is injective. What does that tell us? What fact does that tell us? If we have an injective map, we know something very specific about the null space of T. It's trivial, or it only contains the 0 vector. That's all there is to the null space of that map. Now what I would suggest is thinking about one of your theorems, or a previous proof or theorem. And in particular, I think I looked it up, it's 3.4, and this is the dimension theorem. This is saying the dimension of your domain is equal to the sum of two things: the dimension of the range of T and plus the dimension of the null space of T. Now, theorem 3.4 then says that the dimension of V, the trick now, or the nice part about this is the domain is the same as our codomain. which is not necessarily the case when we first learned theorem 3.4, but here we know the dimension of V is equal to the dimension of the null space of T plus the dimension of the range of T. Maybe I should write that out just so that we're clear. Now, because our map is injective, what do we know about the first term on the right-hand side? We know now that that is 0, so that we now have the dimension of V is 0 plus the dimension of the range of T. But the range of T is going into V. So obviously now the range of T covers the entire codomain, which is also our domain. This now says, thus, this map T is surjective. Or, now what we've shown is that 2 indeed does imply 3 for the second part. And finally, if we go to, let's say, the third part, or part C, we need to show that, or assume 3, and that 3 implies 1. If we now assume 3, if our map is surjective, what does that tell us? So if it's surjective, that means we can cover the entire codomain. Or what do we mean by cover? That means the range of that operator can reach any vector in our codomain. Or we're now saying that the range of T is in fact V, since V is our codomain in this case. Our domain and codomain are the same. Now you can just play that theorem again. That theorem is very powerful. You can say that, oh, from theorem 3.4, that gives us that the dimension of V, which is the dimension of the domain, is equal to the dimension of the null space of T plus the dimension of the range of T. But in the surjective assumption that we're assuming, we know that this dimension of range of T is dimension of V by definition of a map being surjective, and that now implies that the null space of Z, the null space of T, is trivial or has dimension of 0. That now says that our map is not only surjective, this operator, but it's also injective. And once we have a map that's both surjective and injective, we know it's invertible. T, by assumption, is surjective. We assumed 3. We showed by theorem 3.4 that it's injective. And thus, by proposition 317, with our map being both surjective and injective, that was this if and only if it's invertible, the map is invertible. And now we've basically finished chasing our tail. We demonstrated or proved that 1 implies 2, 2 implies 3, and 3 implies 1. Correct. Yes, so the question was, what am I missing? It seems like you just showed 1 implies 2, 2 implies 3, and 3 implies 1. But 1 definitely, from this argument, not only implies 2, but it also implies 3. And that's okay. 1 implies 2, 1 implies 3. 2 needs to imply one of those, and 3 needs to imply one of those. And it can. It's just how do you want to do it? I just extracted one of the pieces that I needed, which was the map being injective, and I didn't use the fact that it was also surjective to show that 1 implies 2. But 1 does indeed imply 3 by that same proposition, Proposition 317. Is that okay? That was your question or comment, right? That was your confusion. Well, hopefully I'm here to confuse. No, I'm here not to confuse, and hopefully you're not as confused now as you were maybe before. But this is a powerful theorem, actually. Now that you are dealing with an operator, all you need to do is, oh, let me find the null space of this operator. Oh, it's trivial, or it's only the zero vector. Then I know that that map is invertible and surjective, and you wouldn't have to find it necessarily unless you were asked to invert the map. Yes? So the question was, if I give you an operator, I'm rephrasing this differently just so that I understand your question. If I hand you an operator, is it invertible? No. No. So we don't guarantee that if I give you an operator, it will be invertible. You have to determine whether it's invertible. But once it's invertible, then it's injective and surjective. Or if you now tell me, oh, is this the operator you're giving me? Let me go look. Oh, it's injective. Well, then it's invertible and surjective. But all operators are not necessarily invertible. They may have non-trivial null spaces. They may not be surjective. Okay? But if you show one of those three, you have the other two. So we were talking or giving money away before class started. Now if somebody hands you $1, they're actually giving you 3. Sort of, right? And I said that I would talk to you after class. Oh, this is being recorded, isn't it? Other questions? You're making me incriminate myself. Now what I want to do is move on, obviously. That's what I want to cover for Chapter 3. That's what you need to know for Wednesday, for exam number 1, is the material that we've covered up to this point. Now, don't fall asleep, but now we're going for exam 2 and the final. Okay? The final will be comprehensive. So you can't forget after Wednesday what you're learning from the first of the semester. Now what I want to do is simply, and I'm going to just scroll through these, what you might do is just write down the proposition or the theorem numbers. These are all from the second edition. But I want to just quickly remind ourselves of what we know or what we understand about polynomials. And obviously this will help us when we start talking about different parts of these operators. These operators might produce polynomials. And that's what we want. That's why we need to understand these. And our operators, depending on what field we are playing in, whether we're playing in the field of real numbers or the field of complex numbers, that determines what kind of eigenvalues we might have. We might be playing in the field of complex numbers and have all real eigenvalues for that operator. That's okay. They don't have to be complex eigenvalues. But if we're playing on this field of reals, then we can't get into the complex, and if our matrix has complex eigenvalues, then we can't say that it has, well, I'm getting ahead of myself with respect to factoring and other properties of matrices, but let's play now with polynomials. I gave you a little bit of time to maybe copy some of this down, but I hope that we feel comfortable with P of z. P of z, let's say, is this Michigan order polynomial, but it could be living in the field of all polynomials, or I'm sorry, in the vector space of all polynomials over the field F, where F in general can be either real or complex, but a lot of times we specify. This is now on the reals, or this is now on the complex numbers. Proposition 4.1 tells us about roots of a polynomial. Lambda, living in R or C, is a root of P of z if and only if you can pull out from P of z this factor z minus lambda and leave this remaining polynomial that's obviously of one order less than P of z. Q of z is a lower order polynomial. Question? So now you could say that the question was, is Q of z a subspace of P of z? And you could, in the way that we've talked about subspaces. So now you could say that Q of z is this subspace. It's now an Michigan minus 1 dimensional polynomial, and that is a subspace in this Michigan size set of polynomials. Maybe that's not how you've thought of polynomials in the past, but you don't need to necessarily, but it's nice to have that understanding. That's what we mean by a root. You need to be able to factor out this factor z minus lambda. And when we're dealing with the field being reals, that isn't necessarily always guaranteed for a generic polynomial. And we're going to see that in a minute. This tells you something different. This is the fundamental theorem of algebra. Wow, this is big, okay? The fundamental theorem of algebra. What does that say? This says that if I give you a polynomial that is not constant, so P of z isn't equal to 6, P of z is not equal to 27, or P of z is not equal to 368 times pi, that would be a constant. If it has a z in it, but now we have to say our field of numbers are the complex numbers. Living with this field, we're not special. Now z and all of our coefficients can be complex. If you allow P of z to be non-constant, a non-constant polynomial with complex coefficients, then we're guaranteed that that polynomial has a root. But we have to make sure that we're living on the complex number field. If we have a real, if we're on the reals, we're not guaranteed that a generic polynomial will have a real root. That's a big deal, actually. That's why they're calling it the fundamental theorem of algebra. Here is sort of the other side of that. This is theorem 414, and now we're dealing with reals, real coefficient, real variables, and now we have real and quadratic factors of the polynomial. Meaning there are polynomials with real coefficients that we cannot factor into all linear factors if we want to preserve real coefficients in that factored polynomial. Meaning these quadratics, they are the pieces of this underlying polynomial p of x that do not possess real roots. You could factor those, but they are going to have imaginary roots. And that's not living in our real numbers. So we can't factor them any further. We may be stuck with quadratic factors. Here we're saying we have Little Michigan real factors, and then we have Capital Michigan quadratic pairs of factors beyond that. And what I would have you think back to is just the quadratic formula. Suppose that we have one of those quadratic factors. Here I'm just leaving it as a generic subscript, x squared plus alpha sub I x plus beta sub I. In this theorem of 414, this is saying when we had this particular relationship on alpha and beta, if alpha sub I squared is less than 4 beta sub I, then those are not factored into real roots or linear factors with real roots. If that's the case, then these quadratics can't be reduced in size or in order. We have to stick with quadratic. Meaning, in this one single quadratic factor, x squared plus alpha sub I x plus beta sub I, if I said find the roots, you would use the quadratic formula in general, let's say, not your calculator. You'd probably pull out your calculator and just have it factor it. But that now is this minus alpha squared, and typically if you said your quadratic was ax squared plus bx plus c, then it's minus b plus and minus b, the square root of b squared minus 4ac over 2a. Here we don't have an a, our b is alpha, and our c is beta, but doing the same thing, we end up with this discriminant. And if that discriminant was less than 0, then we would have a negative number underneath that radical, and we would have complex roots to that quadratic. And that's actually the condition in that earlier theorem. If alpha sub I squared is less than 4 beta sub I, then that quadratic would result in in complex roots, and that doesn't live in the set of real numbers. And so we can't break that polynomial p of z or p of x down any more than those quadratic factors or terms. Questions on that? That's chapter 4. That's it. All right, chapter 5, chapter 6, chapter 7. I knew we would get, yes, final exam. Take out a piece of paper. Make sure it's blank. You may turn in a blank piece of paper. That would be easy to grade. But you may not like the result. All right. Let's move on. Chapter 5. Now let's work with eigenvalues and eigenvectors. And now what are we using? Now we are assuming that we have operators. Our domain and codomain are the same vector space. We're now working with operators where this matrix A is square, and let's say it's n by n, and its elements are coming from the field F, where F again could be either reals or complex. A is then, because it's a operator, is in fact a square matrix. The concept today that we want to try to appreciate or better understand is, suppose that I present you with the following relationship or equation. You now have this matrix A. Suppose that I say, oh, I can actually find a vector x and a scalar lambda such that A operating on x is equal to lambda operating on that same x. X is a vector. This x, so that's where you could get confusing. These are overloaded, a lot of these terminologies or terms. Question? The operator A, or now the operator is represented by a matrix A. And this matrix A is taking as its domain some vector. Let's say it's n-dimensional. That's where the little n, Nevada, comes from. And it's mapping that into a codomain, which is the same, which is another n-dimensional vector. So the matrix A is a element, it's a matrix that's n by n in the field of F. So the elements of A, which is a square matrix, is mapping from a vector that's n-dimensional that has elements in F to a corresponding vector X that's n-dimensional that also has elements in F, where F could be the reals or the complex numbers. Yes, so X and A, they have to be compatible, right? You can't make AX mean anything unless X is how big? It has to have n rows equal to the n columns in A. X is a vector with coordinates, and a lot of times will say elements, coordinates in our field of numbers F. A is this matrix that has elements in F, and lambda is a scalar that lives in F. This is the concept. Now we're saying we have a matrix A, and that operates on a vector. And that process then says, oh, that result is like we stay in that same vector, we just scale it by a scalar lambda. And that relationship now is what we will use to define our eigenvalues and eigenvectors. If we have this equation satisfied, ax equal lambda x, if x and lambda exist, then x will be called an eigenvector, and lambda is an eigenvalue with respect to A. So with respect to this A, which is a matrix representation of some operator, some linear operator, we've now identified an eigenvector and an eigenvalue for that matrix A. The operator takes a vector. Here I'm just going to try to, in words, say what we were talking about before. The operator takes a vector and maps back into a scaled version of that same vector. Or now put yourself in a three-dimensional real environment, which could be this room. Identify some origin. We are now in 3D space. the operator's action, or the result of mapping x through that operator A, the operator's action keeps the original point in 3D. The original point is this vector x. You can say, oh, here's x in this three-dimensional space. The operator's action keeps the point in 3D space on the same line as it started on. Here I'm assuming that we have a real eigenvalue and a real eigenvector. Now maybe here is the point x, and now you'll just have to visualize this if you're listening to this, but just visualize a point in your room. Now assume that you have some linear map that operates on that point. If it's a particular vector, and in specifically it satisfies that previous equation and it's an eigenvector, then going through that map, you're going to stay on that same line. You just may be at a different location on that line because it's scaled by this real eigenvalue lambda. If lambda is -2, then it's reflected, it's scaled by a factor of 2, but it's now opposite the origin on that line. If your eigenvalue was 5, now you just move up that line a multiple of 5 from where you started, but you're on that same line. Let's look at this concept of eigenvalues and eigenvectors via some examples. Example 1. Suppose that I give you a matrix A1 that's -1, 0, 0, -2. And you should be so lucky if I give you that and tell you to pull out a piece of paper and start talking about eigenvalues and eigenvectors. You just should start whistling and feeling really good, because what are your eigenvalues? This is a diagonal matrix. Your eigenvalues are on the diagonal. They're -1 and -2. A1 is a diagonal matrix. Which is very special. Or you could say it's a nice matrix operator. Now, let's assume that we don't know all there is to know about eigenvalues and eigenvectors, and suppose that we think about a vector v1. Suppose that that vector v1 lies on the x-axis. Suppose we let v1 be sort of this standard vector of 1, 0. The first coordinate is 1, the second coordinate is 0. That represents a unit position in the x direction. Now let's look at what happens when we operate on that vector with this matrix A1. Now we have -1, 0, 0, -2 operating on 1, 0. And what did we talk about last time? When we say post-multiplying by a vector, what's that vector actually doing? It's scaling. All of the coordinates of that vector are scaling the corresponding columns in the matrix that it's operating on. In this case, that 1, 0 is simply extracting the first column from that A matrix. The product of this A1, V1 then says, oh, I do not want any of the second column, and I want all of the first column, and scale it by 1. I now have -1, 0. That's now my output of taking this vector v1, my input vector, and mapping through the matrix A. But we can rewrite that output as a scalar minus 1 times our original vector v1. And now what do we have? Now we have this eigenvalue eigenvector equation that we talked about at the first, or just recently. In words, the resulting output vector where does the output vector live? X-axis, y-axis, xy plane. Where is our output vector? It's minus 1, 0. If you had to go map that on a plane, we're just playing in the plane now. That's still on the x-axis, isn't it? It's just opposite the origin from where we were. The resulting output vector stays on the x-axis. But now, where are we relative to where we started? We haven't moved any further away from the origin. We've just flipped through the origin. So we've scaled by 1, but changed the sign. Our output is scaled by minus 1 from the input. Suppose we look at another vector, v2, and suppose it lies on the y-axis. And to make our thinking easier, let's just assume that it is 0, 1. So that now if I look at A1, V2, knowing what we know about how to do this matrix vector multiplication, we're simply going to extract the second column and scale it by 1. But that's just minus 2 times where we started. In this case, our output vector, it's stuck on the y-axis. It didn't move, but it did get scaled. Output vector stays on the y-axis. It's now scaled by minus 2. So now we are further away from the origin than when we started, and we're opposite the origin, but we're still stuck on the y-axis, depending on where I am. But we're in the xy plane. What are some comments that we can make relative to this first example, example 1? One is the initial vectors, v1 and v2, were actually eigenvectors. Initial vectors were eigenvectors. Why can I say that? Because we started on a vector and we stayed on that same vector. And those vectors were really subspaces in our domain. So that subspace is invariant. We're not moving off of that subspace when we map through A. So V1 is an invariant subspace to that operator A1. V2 is an invariant subspace relative to that operator A sub 1. Those are invariant subspaces, and those are actually then eigenvectors. The scaling quantities were eigenvalues. In this example, our A matrix was a 2 by 2 matrix of real elements. Little n was 2. And for this A matrix, maybe I should say A1, we had 2 eigenvalues, which is obviously related to little n equal to 2. We had 2 eigenvectors. Our scaling was actually real. And one of the reasons we could see all of that happening was because this A1 was diagonal, purely diagonal. All the off-diagonal elements were 0. A1 was diagonal, which really says that the eigenvalues were the diagonal elements. Meaning if somebody gives you a diagonal matrix and maybe that matrix is living on the field of real numbers, all you have to do is look at the diagonal elements and those will be your eigenvalues for that matrix. Your eigenvectors will be the standard basis for that particular matrix. Let's look at a second example. Suppose A sub 2 is now minus 1, 1, 0, minus 2. This is now an upper triangular matrix. What comments can we make for this matrix? Can you tell me anything about the eigenvalues without any computation? Because it's triangular, it could be upper or lower, and upper now means I have everything below the diagonal is 0. If it was lower triangular, everything above the diagonal would be 0. As long as I have all 0 above or below the diagonal, my eigenvalues are still on the diagonal. One of the comments then is eigenvalues are minus 1 and minus 2, just like in the previous matrix, but this matrix is not equal to A1, is it? It's different. Eigenvalues are minus 1 and minus 2. They're still on the diagonal. I could label one of the eigenvalues, lambda sub 1, as minus 1. And it has an eigenvector v1 of 1, 0, just like before. A third comment is lambda sub 2 is minus 2. Here's where this matrix gives rise to a slightly different eigenvector from before. Now v sub 2, the eigenvector associated with the eigenvalue minus 2, is minus 1, 1. That's not the y-axis anymore. If I gave you this on exam 2, how could you tell me that this eigenvalue-eigenvector pair is legitimate? Just plug them into that formula. What if we do a verification then? Let's convince ourselves that indeed what we said is the eigenvector is the eigenvector. So now we have a sub 2 v sub 2 minus 1, 1, 0, minus 2 times minus 1, 1. And what's that? Now we scale the first column by -1, and we add to that the second column, so that now we have 1 plus 1, and we have 0 minus 2. And that becomes 2 minus 2. And that vector then is, if we factor out a -2, that's a -1, 1. Which is now this -2 v sub 2. And there's our verification. Now we had a slightly different eigenvector for the same eigenvalue, but our matrix A sub 2 was slightly different from the all diagonal A sub 1. Let's look at a third matrix example. I told you this was going to be a day of examples. Example 3. Question? So now the question was, do these eigenvectors have anything to do with the basis vectors? So now the basis vectors are, well, what are the basis vectors? Getting ready for exam number 1. If I gave you R2, what would you give me for a set of basis vectors? Did everybody hear that? A lot of you said, I think, the x-axis and the y-axis, or the standard basis. That wouldn't have to be. I could give you another basis as long as it spans R2. So the basis vectors right now are not related necessarily to the eigenvectors. The eigenvectors are the direction that this operator likes, is how I like to think of it. It favors this direction. It favors meaning that it prefers, well, I don't know, it likes to stay there. It's invariant. You've now found a vector, v1, in A2 that says, oh, A2, I like the x-axis, because if I start on the x-axis, I'm going to stay on the x-axis. The other one is what? Now I'm going over -1 in the x and up 1 in the y. Is that aligned with the x-axis? Is it linearly independent of the x-axis? So it spans, so you could view these as basis vectors of R2, but we haven't said anything about basis vectors. We're just saying these are vectors that A2 likes because they are actually invariant subspaces for this particular operator. Question? So yes, given this set of eigenvectors, you could use these eigenvectors as a set of basis vectors. There's no unique set of basis vectors for R2, but somebody might say, I want you to make this operator look nice. Then you might want to try to find these eigenvectors and then use those as your basis vectors, and that's going to start infusing a lot of zeros in your transformed representation of this operator. And this transformed operator is going to what? Ideally, you would always like it to be diagonal, because then it's easy to know what's happening. You always know how you are scaling and where you're moving relative to those eigenvalues. But we're getting ahead of ourselves a little bit. Let's now look at B. Whoops, what am I calling? Oh, B. -3/2, -1/4, -1, and -3/2. This looks more like an exam problem. Now, by inspection, what are the eigenvalues? Or maybe the first thing you want to say, does B have any real eigenvalues. What do we need to have happen if B is to have real eigenvalues? What do we need to be true? If B has real eigenvalues and eigenvectors, it has to satisfy that equation that we just used at the beginning of the class. It needs to be such that we can find a vector x, which when operated on by B, leaves us in that same subspace or in that same direction, just scaled. We need Bx is equal to lambda x. Let's see if we can now find such x and lambda. But what's lambda? It's a scalar. What's x? X is a 2 vector, isn't it? So now let's create a 2 vector with the appropriate coordinates. Suppose we let x be x sub 1 and x sub 2. Then we can look at bx. So now the question from the back was, do the eigenvectors have to be real or the eigenvalues have to be real? So now, are the eigenvalues real? We don't know. We are starting right now with real numbers making up the elements in our matrix B. We are going to determine whether or not we have real eigenvalues or we don't. Somebody might say, you need to either have real eigenvalues or we're not going to talk. Or they might say, here's a matrix, tell me what the eigenvalues are. And then you might see, oh, some of these are complex. Oh, no, they're real. You could compute them, and that's what we're going to do. We're going to see, does this matrix even have any eigenvalues that are real? Right. It doesn't matter unless I say what's the field that we're playing on. And I haven't yet said that, but I'm really sort of saying, let's pretend we're playing in the real numbers. Does this allow us any eigenvalues in the reals? Let's see if we can answer that question. Now, with this parameterized vector for x, we now have whatever b was, minus 3/2 and minus 1/4, and minus 1 and minus 3/2 times x1, x2. And we want that to be some scaled version. That's lambda. And in this case, we're seeing, can lambda be real and still leave us in that same direction, x1, x2. Well, this now gives us two coordinates, x1 and x2, in two equations, and we have this other unknown lambda. Can we somehow find a lambda that will satisfy these two equations in the two unknowns, for example, with x1 and x2? Now, from the first row of this equation, we're going to have two equations. We now have minus 3/2 x1 minus 1/4 x sub 2, and that's equal to the right-hand side, which is lambda x sub 1. The second row of equations says that we now have minus x1 minus 3/2 x2 is equal to lambda x sub 2. Let's now collect our x's together. We now have minus 3/2 minus lambda times x1 minus 1/4 x sub 2 equaling 0. And I'll call that equation A for future reference. The second equation says I now have minus x1 plus minus 3/2 minus lambda x sub 2 is equal to 0. And let me just go ahead and solve that second equation for x1. x1 is now minus 3/2 minus lambda x sub 2, and I'm going to call that equation B. They're my two equations, A and B. Is it clear where they came from? Those are just coming from bx equal lambda x. And we're trying to find the x and the lambda. Let's now substitute equation B into equation A. So that now we have minus 3/2 minus lambda. Now we need to get rid of x1 and just have one x sub 2 in there. We now have minus 3/2 minus lambda x sub 2 minus 1/4 x sub 2, and that's equal to 0. Or we can pull out x sub 2 from all of that, and we can see that we now have minus 3/2 minus lambda squared minus 1/4 x sub 2 equals 0. Pardon? So now we could either have x2 equal to 0, which is a trivial solution. We really don't want that. What we want is a non-trivial x2, a non-zero x2. If we want a non-zero x2, then we want that bracketed expression to equal 0 in order for this to be a valid equation. And what we're asking now, is there a real lambda, or a real number for lambda that will satisfy or solve that equation? Is there a lambda belonging to the reals such that expression in this bracket is in fact equal to 0? And that's really just a quadratic equation in lambda. And we could now say, when is minus 3/2 minus lambda squared minus 1/4 equal to 0? Or when is that quadratic factor equal to 1/4? Is another way of viewing that. We now have a quadratic equation, and I'm going to solve it maybe a little differently than what you might. I'm not going to multiply it out and use the quadratic formula. Let me just kind of look at this. I now have minus 3/2 minus lambda squared is equal to 1/4. I can take the square root of both sides, and the square root gives me a plus and minus root, meaning I now have minus 3/2 minus lambda equaling plus and minus the square root of 1/4 is 1/2. And now I can solve for lambda. Lambda is now minus 3/2 minus plus 1/2. Or that's minus 3/2 minus 1/2, that's minus 2. And minus 3/2 plus 1/2, that's minus 1. So I have a minus 1 and a minus 2. That silly B matrix had the same eigenvalues that we had in the previous two, A1 and A2. What are the eigenvectors? Now, did you already by inspection anticipate that? Did you anticipate that B matrix having those particular eigenvalues? We didn't even know if they were real, did we? Until we went through this analysis. Let's now see where the eigenvalues live. I'm sorry, the eigenvectors. We now know that minus 3/2 minus lambda times x1 minus 1/4 x sub 2 is equal to 0. And we also know that minus x1 plus minus 3 halves minus lambda x sub 2 is equal to 0. So that now if we put that into a matrix form with our unknown being the x1 and the x2, we would have minus 3 halves minus lambda and a minus 1/4. We would have a minus 1 and a minus 3 halves minus lambda operating on x1 and x2, and that will give us the 0 vector. I'm just rewriting those two equations in a matrix vector expression. Now, if we look at this, that is actually the original B matrix minus our unknown scalar, lambda, times the identity. We've just subtracted lambda off the diagonal terms. And what are we saying? We're now saying, now we need to start thinking in terms of these concepts that we've been talking about. If a non-zero vector x exists that satisfies this equation, what are we going to call that vector x, or where is it going to live? We now have a matrix times a vector giving us the 0 vector. That vector x is in the null space of this b minus lambda I. This vector x, if we can find it, x, is in the null space of b minus lambda I. Or we could write that as x is an element of the null space of b minus lambda I. But we already know the lambdas. We just found those. So if we put in those specific values of lambda, then that would tell us, do we have specific directions for x relative to each of those specific lambdas, lambda equal to -1 and lambda equal to -2. Let's look at lambda equal to -1. If we plug in lambda equal to -1, then we end up with -1/2, -1/4 in the top row, and -1 and -1/2 in the second row. And what maybe it's not obvious, but if you just look at it a little bit, can you see a relationship between those columns? Are they linearly independent? No, they're actually a multiple of each other. These are dependent. Columns are dependent. And that should just be making us go ding, 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 because that says that we can find non-zero scaling values that will combine those to give us the 0 vector. If we have columns that are dependent, then they're linear combinations of one another, and we can scale those via x1 and x2 to make us, or make that combination equal 0. If they were linearly independent, the only values for x1 and x2 would be 0, and that would say, oh, we have a trivial null space. But this now, we've picked this expression. We now need to find a non-trivial vector or vectors in the null space of b minus lambda I. If we now do that, well, let me just say now that this says that the null space, since we have dependency among the columns and the rows for that matter, the null space is non-trivial. Suppose we just pick one of those coordinates. Suppose we just let x1 equal to 1. Then we have -1 times 1, -1/2 times x sub 2 is equal to 0 from the bottom row. And this now allows us to find x sub 2. X sub 2 is what? Minus 2. And that will now make that equation true, meaning the eigenvector associated with the eigenvalue of minus 1 is now 1 minus 2. And that's not the same eigenvector that we had in A1 or A2. Let me now just give you the next eigenvalue-eigenvector combination. Suppose that I now said that lambda sub 2 is equal to minus 2, which we know it is. Well, we get dependency, but let me just write down that this gives us, let's say it's not the same vector, let's call it x hat, is now 1, 2. You might show that, and then we will start after the exam with another 2 by 2 matrix that has real entries or elements that does not possess real eigenvalues. It will only have complex eigenvalues. And we'll learn what that means or what we can do with that after the exam. We'll pick up at that point in a week.